All right, we're on lesson 6.3, which is all about conditional probability. This is our last video for Unit 6. First thing we have to get out of the way is the vocab, which is what is conditional probability? Now that's just the probability that one event will happen, assuming that another event has already happened. So it kind of changes our probability overall. Now, sometimes it might be easier to kind of take a step back and look at exactly what is happening, either on a table or with a Venn diagram, to see what these conditional probabilities are doing, but there are also ways to calculate them with formulas. So let's go over a little bit of how conditional probabilities work and what they mean. So conditional probabilities reflect how the probability of an event can change if we know that some other event has occurred or is occurring. So for example, the probability that a cloudy day will result in rain is different if you live in Los Angeles than if you were to live in Seattle. Okay, they mean something different. So given that you live in Los Angeles or given that you live in Seattle, the probability will change on whether or not a cloudy day means rain. Now, our brains will effortlessly calculate conditional probabilities, updating our degree of belief with each new piece of evidence. So you naturally change what you think given something that happened before. So let's look at kind of what this means or how this looks given a Venn diagram. Now in this example, we're looking at rolling a die. So when you roll a die, you can get obviously 6 different options, 1, 2, 3, 4, 5, or 6. Now, this example, we know that the probability of getting an even number on the throw of a die is 0.5 or 1/2. So when you roll an even number on a die, it'll happen half of the time. We'll call this event A. Now suppose that we throw the die and the result is a number that is 3 or less. We'll call that event B. So what are the odds or the probability that B will happen? Well, again, that would be 1, 2, or 3 out of the 6 possible totals, so 3 out of 6 is also 1/2. So when we're looking at these Venn diagrams, notice that for event B, that's again rolling things that are 3 or less. 1, 2, and 3. These are the possible things. For event A, we want even numbers. 2, 4, and 6. Those are the only things that work. Okay, so out of the 6 numbers, 3 of them count for A, 3 of them count for B, but only 1 of them counts for both A and B. 2 is the only number that is both even and 3 or less. Okay, so the question is, would the probability of observing an even number on that particular throw still be 0.5? So given that I'm telling you we're only looking for numbers that are 3 or less, is it still a 0.5 or 1/2 chance that we get a number that is even? Now the answer is no in this case, because with the introduction of event B, we've reduced our sample space from 6 ways to do it to only 3 ways to do it. So in other words, with the introduction of a particular condition, event B, again saying we only want numbers 3 or less, we've now changed it from being there's 6 things possible to 3 things possible, and again only the 2 here works. So it changes our probability from being 3 out of 6 to being just this 2 will work. Now the Venn diagram below, or off to the sides here, shows us what this all looks like. Again, A given B, but let's see exactly how it all works calculated out. The only even number that works in sample space B is the number 2, which we kind of discussed already. We can conclude that the probability that A occurs, remember A means rolling an even number, so the probability that A happens, given that B has already happened. If I told you for sure that we're only looking at numbers 3 or less, that means given B, we want to know A. If we are given that it's 3 or less, we want to know how many of them would be even. We would write this in this way: probability of A given B. When it has this up and down line, that just means given. So the probability that A happens given that B has already happened. So in this case, we would say in the end it comes out to be 1/3. Now why is it 1/3? Well, it's because if we look at B, given that B has already happened, there are only 3 ways for that to work. We want just one specific one out of B, the even numbers. There's only one number that is even that also is less than 3. So we would say that probability of A given B is 1 out of 3. So it's a 1/3 chance. It's no longer a half chance, a 0.5, that we would roll an even number, because now we're putting on that extra condition that it has to be 3 or less. So it's a little bit easier to see it when we think of it as a Venn diagram, but we can also calculate it using formulas. If we have A and B again as our two events, and we're going to keep them the same. We're going to keep them as being A meaning the even numbers and B meaning 3 or less. So if we wanted to show a systematic way of calculating this conditional probabilities, we would take the ratio of the probability of the part of A that falls within the sample of B, so that both of them happen together. You can call that an intersection, or you can think of it as A and B. And when we look at this, there's only 1/6 of all of our things that work. 2 out of the possibilities of 1, 2, 3, 4, 5, and 6, only 2 is the number that works for both A and B. Okay, so we take the ratio of that, getting the 2, 1/6, over the total probability of the reduced sample. So that's again the probability of B. So we wanted the probability of, A and B, which is just 2, which means 1 out of 6, out of the whole probability of B. Now there are 3 of them in here, 1, 2, and 3. So we'd call that 3 out of 6. So 1 out of 6 over 3 out of 6 is how that would work, or how it would look. Now, again, there are a couple of different ways to write this. We're going to calculate the conditional probability that event A occurs, given that event B has already occurred. Again, we're just taking the ratio of the probability that both happen to the probability that just B happens. So you can write it out like this: probability of A with this upside down U, that means the intersection, so A and B, or you can just literally write it out, A and B, over just the probability of B. Now again, we said that A meant getting an even number and B meant getting a number that is less than or equal to 3. So what's the probability that it's both A and B? We said before on this slide it's 1 out of 6 over 3 out of 6, because that was the probability of getting B. So when we spell it all out, it looks like this. Probability of A given that B happens means the probability of A and B over probability of just B. What ones work as getting A and B? Well, it's just 2. So what's our probability of getting a 2? What ones work as the probability of getting B? So that was 3 or less. Well, that's probability of 1 plus the probability of getting a 2 plus the probability of getting a 3, because all 3 of these ones work. So 1/6 plus 1/6 plus 1/6 means 3 out of 6 would work. So like we had already written down, it's 1 out of 6 divided by 3 out of 6. Now, you can type that into your calculators as 1/6 divided by 3/6, or remember that if we're working with fractions and we do 1/6 divided by 3/6, when you are dividing fractions, write this in red now, it's the same as multiplying, so we call this multiplying, by the reciprocal. We flip these two around. So we'd all of a sudden have 6 over 3. Okay, when you divide fractions, it's the same as multiplying by the reciprocal. When you do this, this comes out to 6 over 18, which of course can be reduced to 1 over 3. So the probability of A, given that B was already a condition, is 1/3, which is exactly what we calculated out before. So it should all work out. So let's look at using the conditional probabilities of 2 events using a table. Now this is going to help us kind of think of them in a more intuitive way. We will just see individually, like each box, how things work. Now this first example, I'm going to let you know, is actually not conditional. We're not looking at conditional probability here. We're looking at a more specific event. So for this example, the students at a high school were asked to name their favorite lunch entree. The results are shown below. So in this column, we have what all the freshmen said. Now, here's the total number of all the freshmen, the total number of all the sophomores, juniors, seniors, and here's the total of all the students in the school. Now, again, this column is just freshmen. This row is the ones who said they like pizza. This row is the one who said hamburger. This one This row is the ones who said burritos. So if I'm looking at, say, this number 100, what is that telling me? Well, it's telling me there's 100 sophomores who liked hamburgers the best. That's what this little data set or this area is telling us. So it lets us get a little more specific. So getting rid of this here, if what we are looking for is the probability that it's a senior who prefers pizza, well, we would just look at all of our spots. We'd say, where are the seniors? Right here. Where are all the people who prefer pizza? Right here. So they've already circled it. It's 85 seniors who prefer pizza. So we put in 85 on top of our probability. Now, if we're looking for total, we're looking for the total of all the students. It never said that we're looking for a probability of someone who likes pizza given that they're a senior. We never said probability that they like pizza given they're a senior. We just said we wanted the probability of a senior who does prefer pizza. So it's the 85 over the total amount, 1130. So this question is actually easier than it looks. It's literally just asking us to find seniors who like pizza over the total. Okay, so we would get 85 over 1,130, which reduces to 17 out of 226. Again, this is not conditional because we didn't say given that they were a senior or given that they like pizza. This is just a very specific event. Seniors who like pizza out of the total. Let's look at another example. Again, this one will not be conditional. It's just a little more specific. In this case, we're looking for the probability of it being a senior or a student who prefers burritos. With this additional or word, this means all of these seniors will work, so this total right here, and that they prefer burritos. So we want the total of all these people who prefer burritos. Now the problem is, if I count up all the seniors and I count up all the people who like burritos and I add them together, that means I counted some of them twice. I counted the ones who are both seniors and like burritos. I counted those people twice in that same group. So when we're looking at it, we have to break it down into how many people are seniors, which would be 220, plus how many like burritos, well, that's 300, minus how many of them are both seniors and they like burritos. Well, that's this number right here, 70. Now, technically, I should be doing this as probability. So each one of these should be out of our total of 1130, out of 1130, and out of 1130. So on your calculator then, it'll just be out of 1130, you can just plug these in and find out what our probability of picking a student who is either a senior or they prefer burrito. And when you do that, you should get that it's 450 people who are both, or should I say, either seniors, so this 220, or they like burritos, but we can't double count them. So we have to get rid of at least one of that group of people who are both. We'd get 450 out of 1,130. Now also at the end, you would want to reduce that if you can, so that would become 45. We can just divide 10 out of each, out of 113. So the probability of getting someone who is a senior or they're a student who likes burritos would be 45 out of 113. So you kind of have to be careful of, is this a condition or is this just being specific? Now this is not conditional, it's just a specific event. Now this one is a conditional event. We can tell because it has this bar right here up and down saying we want to know what's the probability of picking a freshman given that it's a student who prefers pizza. So if we're looking at the total of people who like pizza, that's no longer the total of all of our students. We're just looking for the total of people who like pizza. So 300 is now our total amount. Now, if we wanted the probability that they are a freshman, given that they prefer pizza, we would just find freshmen who like pizza, which is 90, and that would be what we put on top. So 90 out of 300 would be our probability. To reduce that, though, it would become 3 out of 10. So, given we're only looking at students who prefer pizza, what's the probability of picking a freshman? Well, it's 90 out of 300, which is the same as 3 out of 10. So this example resembles our conditional notation. It only works, this 90 only works for the people who like pizza. So it changes our total amount. Okay? Because we are given that they prefer pizza, our total number of students to pick from is no longer this 1,035, it drops to this 300. Now, we also need to be aware that this, so the probability of picking a freshman, given that they are a student who prefers pizza, it's not the same at all. Cross out, it's not equal to students who prefer pizza, given that they are a freshman. So the difference here is, if I say, given that they're a freshman, we'd have to think, whoa, how many total freshmen are there? Well, there's 290 of them. How many of them are freshmen who like pizza? Well, that would be 90. There are 90 freshmen who like pizza out of 290 freshmen total. That would reduce down to 9 out of 29. Oops, 29. Now, 9 out of 29 is not the same as 3/10. Okay, so it's very, very important which one goes first. When you write it this way, this word out front says, what's the probability of this, given that this thing was already true. Okay, so it always definitely matters which one comes first. And that'll actually be it for our last video of Unit 6.